So far, we have established a phase transition in the GNP graph model for the items such as disappearance of isolated vertices. In that, what we have did, we have introduced a random variable x was a number of occurrence of that item, and then we determine the probability p for which the expectation value of x went to 0 at infinity. For the value of p where the e of x will tends to 0, we argue that the high probability a graph generated at a random had no occurrence of the x. And for the value of x where e of x will tend to infinity, we use the second moment argument to conclude that the high probability and the graph generated at the random had occurrence of x. That is, occurrence of a force e of x to infinite were not all contracted on vanishing a small fraction of the graph. One might raise the question, for GNP graph model, do there exist items that are concentrated on small fraction of a graph that the value of p where e of x goes to 0 to infinity is not a threshold? So if the value of e of x is going from 0 to infinity, in between there is a small fraction of situation where that item will occur, and the situation which we are talking here, it is actually happening into the Hamiltonian circuit or Hamiltonian cycle. So anyone know what is the definition of Hamiltonian cycle? So to understand the definition of Hamiltonian cycle, you should know what you mean by Hamiltonian path. Hamiltonian path in undirected graph is the path that visits each vertex exactly once. I will repeat again. Hamiltonian path in an undirected graph is a path that visits every vertex exactly once. And what is the Hamiltonian cycle or Hamiltonian circuit? Is a Hamiltonian path such that there is an edge from the graph, a last vertex and the first vertex of the graph of the Hamiltonian path. That means it completes a full cycle. And we have seen certain example in which the certain graphs have the Hamiltonian cycle, certain graph does not have a Hamiltonian cycle. For example, I can draw this graph. So if I can say this is the first vertex, second vertex, third vertex, fourth vertex, and fifth vertex. This graph have the Hamiltonian cycle, and that you can see. You can go from 1 to 2, 2 to 3, 3 to 5, and 5 to 4. And then again you go from 4 to 1. That will be your Hamiltonian cycle. But in this graph, if I can draw the graph like this, then this graph does not have Hamiltonian cycle. Okay. because in that case, this vertex will be repeat. So this is about the Hamiltonian cycle, and here we are discussing the case where the E of x is goes from 0 to infinity, that does not have any threshold in between. So for that, let us consider, so what actually we are doing or we are discussing here, what will happen into the Hamiltonian circuit, into the GNP graph model, or what will be the threshold for, obviously we are not going to prove what will be the threshold for, but we'll discuss that, having the Hamiltonian cycle in GNP graph model. So let us consider x be the number of Hamiltonian cycle in GNP graph model, and let consider P be the probability, which is d by n, where d is some constant. Now, what will be the expectation of number of Hamiltonian cycles will be there? What should be this situation? So what is the potential Hamiltonian circuit in the graph? How many potential circuits will be there if it is a only three vertices are there? Here we have n vertices. So if we have a three vertices, how many Hamiltonian cycle will be possible? So
Three?
yeah, it is only three. Not it is actually three, but it is actually one. All other means the cycle which you are talking, it is isomorphic to this.
Yes, sir.
Okay. So if it is a three vertices, then it is only one Hamiltonian cycle is possible. If there are four vertices, then how many Hamiltonian cycles are possible? In that case, it is three Hamiltonian cycles are possible. Can someone draw all the three? The first one is this: one, two, three, four. Any other?
One, three, four, two.
You can go in this way. One, three, four, two. Okay. Is there any other?
One, four, two, three.
One, four, two, three, one. Okay. So these are the possible Hamiltonian cycles we have in this. So here the question is, if it is number of vertices are n, then how many number of Hamiltonian cycles will be there? So it is actually, so there are 1 by 2 into n minus 1 factorial potential Hamiltonian cycle will be there. And each having vertices, each having the ages, each Hamiltonian cycle having the ages is n, because it has 3 ages, it has 4 ages, and so on. So each age having the probability is d by n. So there are n number of ages will be there. So this quantity multiplied by d by n will be the expectation for having a Hamiltonian cycle. So that means expectation of x, we will have it as 1 by 2 n minus 1 factorial into d by n power n. Now what is n minus 1 factorial? That we can see is n factorial. Actually it is approximated. So this n minus 1 by 2 factorial by 2, it is approximated by n by e power n. This quantity is actually come from the name of that identity. It is known as, which is come in, but it is approximation of factorial. Stirling, this is come from the Stirling formula, or it's known as a Stirling approximation. And those who are reading that TY BSc with mathematics subject, they have come across the proof of this Stirling formula. Actual Stirling formula is this: n factorial is approximated to square root of 2 pi n into n by e power n. So n factorial is approximated by this. So here it is exactly the same situation we have, but we are neglecting this pi there, and we multiply n both sides. So this n is also combined with this. So it is actually n factorial you will have. And so we can write down this is by using this Stirling approximation. We'll write this one as n by e power n, t by n power n. And this will gives me d by e power n, because n power n will get cancelled out. Now this is a geometric sequence, that is r power n, or I say x power n. This will tends to 0 as n tends to infinity if your value of x is between 0 and 1. This will tends to infinity as n tends to infinity if your value of x is bigger than 1. This is the quantity might be we have. We already know this. And using this is here in place of x, we have it as d by n, d by e. So this quantity will, I cannot say it is equal to, but it is tend to 0 if the d by e is less than 1. If it is less than 1, it is obviously it is greater than 0 because the value of d is bigger than 0. It is a probability. So the value of d is between 0 and 1, d by e is between 0 and 1, then it will tends to 0. And if it is infinitive, then d by e it is greater than 1. So finally, what we can conclude here, it is the expectation will be tends to 0 if d is less than e, and is infinitive if d is greater than e. Now, what does this suggest? That the threshold for Hamiltonian cycle occur when d is equal to e, that is the Euler number e, or I can say Euler constant e. This is not possible because the graph still have the isolated vertices. Not even it is connected. Because in the previous lecture, what we have proved is that disappearance of isolated vertices having the threshold is ln by n. So what we have proved in the previous lecture is we have a isolated vertices if the value of p is ln by n. If the value of p is ln by n, then still the graph will have the isolated vertices. And still the graph have isolated vertices. And how in this situation we can say that it has a Hamiltonian cycle? Because here we have a probability is p equal to d by n, and the value of d we have, according to this we have chosen e, that is the Euler number. And this is not possible since the graph still have the isolated vertices, and not even the graph even connected if the probability is this. Thus the second moment argument is needed, necessary. So what we are, you need to know that a threshold for Hamiltonian circuit, it is actually a d is equal to small omega log of n plus log of n is there. And we are not going to prove this thing. That means the threshold for Hamiltonian cycle is this. But for asymptotically greater than this value, that is 1 by n of this d. If this is the d, then 1 by n into d. Then DNP graph model have the Hamiltonian cycle with the probability 1. And this is the same threshold for disappearance of one vertices. And clearly the graph with the degree vertex 1 cannot have the Hamiltonian cycle. But it may seem that surprisingly the Hamiltonian circuit appearance as soon as a degree of one vertices will be disappears. That means a degree having the one vertices. That means is a pendant vertex is there. Once the pendant vertex will appear, the probability is this one. Okay, that means the graph will become connected. And soon if you increase the value of p, and soon the graph will become connected and it will appear the Hamiltonian cycle. And that is the situation is actually happening. And this is the reason the frequency of the degree 2 and the degree 3 vertices if in the graph is very small, and the probability that 4 such vertices could occur together, which subgraph is too small for the happening non-negligible probabilities. So that is the things that we need to discuss in this Hamiltonian circuit. So graph will have a Hamiltonian cycle, then its the threshold will be this you have. We are not discussing the proof of this one, but it is important. The next thing is a giant component, which we already have talked in my practical sessions. So if you have considered GNP graph model, as P grows, starting with P equal to 0, a graph has n vertices and no edges. As P increasing, edges are added. So if you increase the value of P, the edges will become added. A forest of a tree emerges, that means it will become a forest. When P equal to order small o of 1 by n, then the graph is at most surely a forest of a tree. That means there is no cycle. When P equal to d by n, and where d is constant, a cycle appears. For d is less than 1, no connected components has asymptotically more than log n vertices. And the number of component containing cycle is a constant independent of n. Thus, the graph consisting of forest of a tree plus few components have a single cycle with no omega log n size component. Of this size component will be there. And if P equal to 1 by n, a phase transition occur when the giant component occurs. So P equal to 1 by n is there, then a giant component's phase transition is 1 by n, which I can say. The transition consisting of double jump, that means if P equal to 1 by n, the component of a size n raised to 2 by 3 vertices emerge, which is at most surely it is a tree. And if P equal to d by n and the value of d is bigger than 1, a true giant component emerge have the number of vertices potential to n. And this is the seminal result in the graph theory and the main subject of this section, that means which we are discussing, that a giant component is also arise when a real world graph, that means some of the graph we can talk about, the reader may want to look at a large real world graph like a proportional of web pages, which we are discussing in the previous lecture, of finding the size of a large component, connected component. So when one look at the connected component for the large graph, the appearance of various contains, once observe that often there are very large components will be there. One example I can give you, suppose you have a graph formed from the database of protein interaction, where the vertices correspond to proteins and edges correspond to pair of proteins of interactions. So it is slightly biological terminology we have, and in that this is the situation we are conducting. That is one of the way is to see the how the proteins interaction is there. So what we are considering as a vertices, we are considering as a vertices as a proteins, and we are considering edges is how the corresponding two proteins that are interact. By the intersection interaction, one means that two amino acid chain that bind with another one for the function. That means there is a two amino acid together is club up, and then it will give you another protein. In that way, the binding is there. The graph has actually, it's, if you can draw this graph, the data is already available in science. There is one paper is published in science in 1999. There was one paper is published due to this, and the data is already there, and in that the graph has 273 number of components of various size. And I can draw some of the figure here. That is, here if I can say size of component, versus the number of components. That means there is a one, size is one, that means isolated vertices there are 18. So they are not interact with any other proteins, mean to say. There are two, it is 79. 4, it is 25. 5, it is 14. 6, 6, 7, 4. 8, 6, 9, 1, 10, 1, 11, 1, 12, 0. Till 15, it is 0. Then it is 16, then it is 1. Still, it is 100, 1851 size. Then it is one component. So there are number of isolated vertices are 48. That means this situation is 48. This situation is 179. Still in between, that is a 3 is left. Oh, anyway, if it is 3, then it is 50. So this is the situation we have into the real problem, real world problem. That is a protein structure we are talking about, how the proteins are interact with each other. And in this, there are number of small components, but there are one component which is very, very large, which I can see that the one component having the size is 1851. So total there are 270, sorry, 2735 number of vertices are there, and there are 306, sorry, 3602 number of edges will be there. Among this, it will have one component of this much size. As more protein are added, the data base of a giant component will grow even larger, and eventually a small up, all small components. So existence of a giant component is not a unique to the graph procedure for this data protein data set which we are talking. It take any data set, you will take any data set, one can convert into the graph. So whatever the data set you will consider, you can do your analysis and you can convert that data set into the graph, and it is a likely that the graph will have a giant component, and provided the ratio of the edge to the vertices is a small number greater than 1. So here I'm just having another example I can give you. For example, we'll say research papers. So in the every day there are lots of research papers are publishing, and we consider the research paper, one research paper as vertices, then another research paper, and so whatever the research papers are there, all of them is as a vertices. and we'll consider ages are the research papers are having the citation into that paper. So suppose I have written one research paper, in that there are 13 or 14 number of research papers are there which I have cited, which I have used them to produce my research work. So that is the, I can say, a link between these two research paper. So in that way we can have the establishment of relation between the vertices and edges. And if you can take this number of this type of situation, the this situation is also available in web. Some of the web pages you can find out, as I have talked in the earlier, that Erdős and Ray's numbers which I have talked, that in that also the same situation is there. And in that, if we can talk about this giant component, then this is the situation. That means 1, 2, 3, 4, 5, 6, 7, 8, 14, and 2, 7, 4, 8, 8. So there are isolated vertices are this much. 459, that means a size 2 is 549. 129, 51, 16, 12, 8, 3, 1, and this one. So there is a one large component is there in this situation also. That is a vertices of our papers, and the ages means that two papers should share an authorship. That also will have one of the as a thing. Another way is to see that by into the English dictionary. For example, synonyms you can say. So vertices represent the word, and the ages connect to the word is the synonyms of the another word. Okay. So in that way, if you can construct the graph, then also you can have in that graph 3,242 number of vertices which compares the giant component. There is another component which is 128 number of vertices in that. That is also one. 125 number of vertices. So there are words which is interlinked with the one word, have the synonyms of another word, and so on. So this is the link is there. And is the size of two graphs which we have constructed from the data sets. And the data set is already available in web pages, some of the web pages, so that we are not interested into. But the question is, or to understanding is, if you have any data set, you can try to convert that data set into the graph by certain relationship, and most of the time that data set have a giant component. So let us returning into the this GNP graph model where P increase, it is beyond D by N. All the isolated vertices are absorbed into a giant component. And when P is equal to 1 by 2 is equal to ln by n, then the graph consisting only isolated vertices plus a giant component. When P equal to ln by n, that is, here it is half of ln by n, here it is P equal to ln by n, then the graph become completely connected. And by, if I can increase the value of P by 1 by 2, then the graph not only connected, but it is sufficiently dense that it has wind of size 2 minus epsilon into L log Ln for every epsilon. So that is the fact that we have, that we are not going to prove here, but I'm just throwing you a knowledge that certain things is there about this giant component. And this giant component is actually very important topic, because as I talked to you, every data set have a giant component, and the property of giant component we already discussed in one of the practical. So how the giant component is appear and all sort of these things we have did. Okay, so